hardware, it goes inside the software. Okay, on the level
Okay.
diagram. And we are just taking outputs from the PLC and giving inputs to the PLC. And all the logic is being implemented inside it. Understand?
Okay. So instead of using too many relays and
Yes.
having one big circuit, yeah.
Yes, basically we are
A small.
compacting things. Okay. So
Okay.
we will learn about it when once we go to the scenarios. You will, realize what we are trying to do over here.
Okay.
Okay. All right. So this is fine until now. Let's go towards the quiz. For the quiz, the first question was that I wanted you to develop AND, NAND, OR, NOR, and exclusive OR gates. So I'm going to develop few of them. Let's talk about the AND gate. If you have any two switches in series, it becomes an AND gate, right? So this is the definition of an AND gate. Let's say if you have S1, S2 in series, A1, basically the operation that you are going to have over here is an AND operation. How you can verify it? You can verify it like this. This is your S1, S2, and this is your A1. If S1 is 0, S2 is 0, that means both switches are switched off. They are not pressed, and your output will be 0. And if it is 0, 1, it means that S1 is 0, but S2 is on. S2 is on, that means if there is a current, it will pass. But there is no current from S1. So output will be 0. If it is 1, 0, same thing will happen. Once I press S1, the current will pass from here. But S2 is not pressed, so current will not continue towards K1. So if there is no ground available, the current cannot flow through the output. So the output will be 0. If it is 1, 1, that means that both switches are on. In that case, the current will pass to K1. In that case, the output will be 1. So this is basically an AND operation. If you are talking about OR operation, so OR operation can be this, one. If two switches are in parallel to each other, you achieve an OR operation. And the definition of an OR operation is like that: if any of the inputs it gets high, the output gets high. So here you can see you have two paths for the current to flow. One is this one, the other is this one. So either one of them gets on, K2 will turn on. Okay. So this is the OR operation. And now talking about exclusive OR or XOR. If you remember the equation of exclusive OR equation is like this: y is equals to a bar d plus ab bar, right? So in this case, A means normally open switch, and a bar over here, it means anomaly. Anomaly close switch. Okay, so we try to implement it. First of all, you have a bar. This is your a bar. okay, and it is being multiplied with B, so it will be an AND operation in B, and then we have plus over here, that means an OR gate. So an OR operation will be performed with A B bar. So A will be open and B over here will be anomaly. We will be using anomaly close switch. Output of this gate will merge over here, and we will have output to 3. That's it. This is your exclusive OR gate. Okay. Okay. All right. Any problem?
No, it's easy.
Okay.
Yeah.
All right. Question number 2. Uh, we did it, I think, in the class also. Um, but let's discuss it. It's better to discuss it. In question number 2, it was about the automation and control of a overhead tank filling level control system using ladder diagram, right? So you had a tank, there were two limit sensors, lower limit sensor and upper limit sensor. So the same thing that we did with the relay logic control, we are going to implement it on ladder diagram. Let me write the heading. Automation of overhead filling system. Okay. So basically, we had two limit sensors and one output, right? The output over here is a pump. So let's suppose the pump is connected to K1 relay, and this relay is basically from Q0.0. All right. And then we have two sensors, I0.0 and I0.1. We have two limit sensors. One is lower sensor, lower limit, and let's say this is connected to I0.0. And then we have upper limit sensor that is connected to I0.1. Okay. Now, the circuit that we made previously, it was like this, that we had a lower limit sensor, it came first, and upper limit sensor came afterward. I think so it was like that. Let's see. Okay, we said that if water tank was fully empty, your sensors are turned off. Okay, so in that case, we can use anomaly close switches. This is your pump, and let's say this is your lower limit sensor. So is your upper limit. Okay. And the pump is being latched with its output terminal. Okay. Now let's see if it is working properly or not. If the tank is fully empty, then both the sensors are switched off. In this case, switched off means that the current will be passing from the this is a normally closed switch. The pump will be turned on. This will once the current reaches K1, this will latch K1. Okay, so the pump will be latched. So the first sensor to switch off will be the lower limit. So this part of the current will switch off, but the other part is available. This part is available, and the K1 will remain latched. So once your upper limit is reached, this part will be broken. Once this part is broken, K1 will be delatched. Okay. So the cycle will repeat again and again and again. Once you drain out the water, upper limit sensor will go high, but the motor will not turn on because no current is flowing from it. And once it reaches the lower limit, it will turn on. And once it turns on, the current will be passing through it. Okay. So this thing we applied, I think, in the previous class as well. I think in the previous class we implemented it with normally open switches. It can be anything, normally open or normally closed. Depends on the sensor that is available in the market. Okay. All right. Now, let me share the other screen so we can talk about this quiz I want to implement on
Sir,
the software. Yeah.
I think you forgot the first push button to start the water flow.
Okay. The
I checked
first
the
push
part
button. Yeah, this can be done.
before the lower limit.
Okay, this can be done.
I think it's okay to edit or remove it, right?
Yeah, it's okay. For now, it's okay.
Yes.
But in the actual system, it should be there.
Okay.
Okay. I will let you know. Maybe we can discuss it right now. There is one thing called MCR. We call it Master Control Relay. Okay. So this master control relay acts like a starting switch and a stopping switch. Okay.
Okay.
This is basically a relay. We develop a circuit, a small circuit over here, which is basically a latching circuit. So let's say this is your one input, and we call it start. And then we have a normally closed switch, call it stop. And then we have one relay. Let's say it's K2, and we name it MCR. Okay, and this MCR is being latched with this normally open switch. Okay, so it is a very good practice to start any logic diagram with MCR. So let's suppose for our scenario, MCR will be connected here. And okay, so once I press the start button, MCR will turn on and it will be latched. Okay, once it is latched, this switch over here and this switch over here will turn on. Okay, now if this switch is not turned on, the system will switch off. Let's suppose MCR is switched off. Uh, uh, and let's say there's an emergency, there's a short circuit, something happened, and due to some reason you have to stop the switch. You press the emergency stop button. In that case, MCR will switch off. Once MCR switches off, the whole operation, the whole machine will go. So usually when building any logic diagram, any network of the logic diagram, you connect MCR before starting any logic. So basically any logic that is being developed in the logic diagram has to be in series with MCR switch. So it gives a safety to the whole system. Let's suppose if I stop the switch, the whole system shuts down. Let's suppose, for example, if the system was running, press the start, MCR is turned on, and this MCR switches, the second network over here, they are turned on. The normal operation of the machine is going on. And at some point, let's suppose I press the stop button. In that case, MCR switches off. Once MCR switches off, this switch over here and this switch over here, they will switch off. Once they switch off, if the pump was running, not running, whatever state it was in, everything will be in shutdown, total shutdown. Okay? No more current will be passing to anything. All the outputs will be shutted off.
Okay.
Understand? So basically,
Yes.
so this is the start and stop operation of any machine. Okay.
And sir, this is all for question number 2.
Yeah, it was a part of question number 2, but I didn't mention it before, so it's not counted for the quiz. Like it will not affect your marks. If your logic is fine, I'm okay with it.
Okay.
All right, no issues. Okay, let me share my other screen so we can see the software that we are using for it. The software that we are using is a TIA photo. So let me open it first. Okay. Once you turn on, something like this will turn on. Okay. This is the window of the TIA photo, version 12. I'm using version 12 here. You can use version 14, 15, whatever is available to you, whatever you try to download. But remember, this is paid software, so you will need to download the correct version in order to run free of cost. So if you want to create new project, you can create your project from here, and you can name the project like let's say overhead tank. Center, it will create the project. After creating the project, once you have created the project, then this window will appear. Over here, you can go to the open project view, or you can configure the device over here. You can always configure the device in in the project view as well. Okay. So let me configure the device from here. Once you select configure the device, you need to add a device. And now here there are three options: controller, HMI, PC. So basically Siemens, uh, they sell their own PC systems for specific machines and HMIs as well and controllers as well. We are talking about the controller right now, which PLC we are going to use. The one that we are going to use is the 7300 and the CPU will be 313C2DT, and this is the exact number that we are going to be using for all these. And once you select this PLC, okay, the description for the PLC is given over here. You can have a look over here that working memory is 128 kilobytes, and at which rate the instruction will be running, how many inputs are there, outputs are there. You can see over here that 16 inputs and 16 outputs are integrated. There are three pulsating outputs like PWM outputs, okay, and there are certain pins which are available for encoder as well. Do you have any idea about the encoders? Anyone has idea about the encoder?
About what?
Encoder.
I only know that
The
it changed from
encoder.
analog to digital.
Say it once again.
I only know that it changed from analog to digital signal.
No, an encoder doesn't do that. Okay, encoder is basically it provides a pulsating output to the controller, and there is a specific stream of pulses. There are two channels for it, channel A and channel B. Okay, this is basically encoder is a sensor, and that sensor is known to determine the position and the speed of the motor. Okay, it's
Okay.
basically connected onto the shaft of the motor, and once the shaft is rotated, the encoder shaft is also rotating with it with the same speed. So that encoder in form of pulses provides the output to the controller, and the controller then determines at what speed the motor is running, and what is if the gears are attached to it, then it will also know the position of the controller as well. Okay, so this is what
So
encoders
I
do.
thought the encoder does the same as in communication. So in
No, no,
communication, we still use encoders that does that. So,
that encoder and decoder is different thing.
yeah.
Okay. So here encoder is different. Uh, if you have later today, maybe anytime, if you have time, check out by writing encoder on the Google and read its description, what it is,
Oh,
how it works. Okay.
Okay,
I'll
sir.
check.
All right. All right. Okay. One more thing. If you have used DC motors, usually there are only two pins coming outside from it, positive and negative pin. Sometimes, sometimes these motors they come with more than two wires. In that case, that motor is basically connected to an encoder. Usually, a DC motor comes with a very small encoder. Um, Maybe let me share the proper screen with you, and maybe I can show it to you. Okay. Okay, here you write with encoder. What you know, this will appear. Okay. Here you see a DC motor and there is an encoder here. There are two sensors, magnetic sensors uh, connected on the PCB. And if you see this round magnet over here, this magnet is basically it has different poles. You know that a magnet has a north and south pole, right? But this magnet, it has multiple poles. It goes like north, south, north, south, north, south, north, south, like this. And as many poles are there, the position or the sensing will be more accurate. Okay, usually there are four. It can be 12, it can be 16, 22, 32, as many it can be. Okay, so based on these pulses, the pulses the sensor will be providing you. There is a specific program for it to know if the motor is running forward or if the motor is running backwards. It depends which pulse comes first. So basically, there is a pulse train. There is a trend of the pulse. If the channel A is high, if the channel B is high at the time, so based on that, the controller knows that if the motor is running forward or backward, or if the counting has to be done in a positive way or in a negative way. So basically, it is an incremental encoder. Okay, there are other encoders as well. Usually, in an industry, we don't connect these motors, right? We connect very huge motors. So for that reason, we use encoder like this. Okay, so the shaft of the encoder is connected to the shaft of the motor, and you will be getting pulse stream. But on the PLC, you will be getting a specific position of the motor. Okay, it will automatically detect everything, all the you can say the pulses, and automatically calculate the position and the speed for you. Understand? So let's get back to PLC. Now we were talking about the description over here, right? Now, okay, this is your PLC, and this PLC looks like this. And the actual model of the PLC physically looks like this. Okay, so once you add this to your project, the next window that is going to open, have it in a few seconds. Okay, this one. So this is the window that you are going to get. So this is basically a DIN rail. On a DIN rail, a PLC is there, and if you zoom in over here, you can see that you have a start, stop, and master reset switch. From here, you can select if you want to run the PLC, if you want to stop the PLC at a certain time. If you stop it, all the program will be stopped. Okay, and these are the status lights. It will tell you in which mode your PLC is in. It is in a stop mode, it is in a run mode, or is it being programmed now? Or if there is an error, it will show you error over here as well. Okay. Now these two over here, the orange and the pink connectors over here are the communication ports. The orange one is basically a communication port for programming. We call it an MPI interface. Okay. This interface connects with an adapter. An adapter connects to a PC or a laptop where you can, from where you can program your PLC. And this pink one over here, this pink one is basically for uh, other multiple interfaces. Like if you want to connect another PLC and an HMI, or if you want to connect more outputs or inputs to the system, so there are some specific cards that can be attached to the PLC. So those cards basically can be connected with this connector. Okay. Hopefully there is no issue. And this section over here is an input output section. On the left hand side you have inputs 0.0 to 0.7, and then again 0.0 to 0.7. So these are 8 inputs and these are 8 inputs, total 16 inputs. And on the right hand side you have 7 outputs here, sorry, 8 outputs here and 8 outputs here. So in total they will be around 16 outputs. Okay. All right. For the information of the PLC's inputs and outputs, you can get from here. Like this thing here. This kind of PLC has the addressing of 124 and 125. Okay. So that means that uh, if you are connecting your input to 0.0, okay, over here, the first input, so you will be addressing it like I124.0, not 0.0. Okay. And similarly, this goes from 124.0 to 124.7. The other section starts with 125.0 to 125.7. And similar is the case with output. The output will be starting with Q124.0 to 7 and Q125.0 to 7. Okay. Now we come towards the program, the ladder diagram. Okay, so on the left hand side, there is a program block over here. Go there on the main. On the main, and now you can see one line over here. There is no other line, but there is a termination point over here. Okay. All right. One thing that I didn't mention in the lecture is that if you address your output, I mean that let's write one program over here. So these are the switches over here, normally open, normally close, and coil. So I'll be writing inputs I124.0, the first input. Let's do the latching circuit first, and this will become I124.1, and it will be connected to a coil, that is Q0.0. Okay, once I have addressed Q0.0, I cannot reuse it again in any network. Okay, so one coil in one network. That coil cannot be tagged again in the program again. You cannot mention Q0.0 again. Understand? Let's suppose that you had two switches. Let's suppose you have two switches that can control Q0.0. I mean that let's suppose this is, you can rename it as S1. This is S2. Okay. Now what I want is that U0.0 can also be turned on using another switch S3. So I cannot do like this, that I introduce 124.2 over here and tag it as S3 and connect an output here and name it Q1, sorry, I mentioned a wrong name over here. This should be Q124.0. I cannot do like this. It may accept over here, but when you compile it, it will give you an error. It didn't, but it doesn't happen like that. There is some issue here. It did accept, but we don't do like this. Okay. 124.0 cannot be mentioned again. The same name cannot be mentioned again. It did accept, but it is not the way to do it. Okay, usually it should provide an error over here. It is not doing that. I don't know why. It shouldn't be like this. Okay, so the thing that we wanted to do, it can be done like this, that you introduce S3 over here, I124.2, that is S3, and connect S3 with this. Now S1 and S3, these are two switches from where Q124.0 can be operated, right? Now we compile it. Once we have done the compilation, we can run the simulator. We start the simulator. Once you start the simulator, this window will open, and with this, another window should open. It didn't. Okay, so there is some problem here. Okay. We go to the PLC. This window will appear. If you don't see PLC over here, don't worry. You can go to device configuration and same thing will open. Okay, compile from here. Compile for this PLC. Now run the simulator. And another window should open with this. Okay, this one. Okay. Once this window is open, you select MPI selector, and the interface that we are using is the PLC simulator. If the adapter is connected with it, you will see an adapter over here. If there is a physical PLC with you, you will see an adapter over here and you can program. Okay, right now we'll be using the simulator. Okay. From here you can flash the PLC as well if it is available physically to you. If not, then cannot. Now you can load this program to your simulator. Once it is loaded, you can run your PLC. Now here you can see the input byte 124 and the output byte 124. All right, and you can also simulate it over here as well. You can see the path of the current when I turn on switch S1 or S2 or S3. This is the monitoring button. Once you switch it on, there will be 3 green blocks here. Once these are 3 green blocks appear, that means your PLC is online and running. And you can see the current, the green color, it represents the current path. So once I press S1, this current will be flowing towards Q124.0. So let's see if it happens or not. Once I press this, you can see it goes to 124.0. If I switch it off, it will be switched off. And if I press 124.2, so there is another path for the current to flow to Q124.0. Understand? Okay. If we want to flush the relay, okay, if you want to turn on, return back to the programming, then you need to stop the PLC go offline. Once you go offline, you will be returned to the programming site. Now you can do the program. For latching this relay, you can use the normally open switch of this Q1 24.0, right? And we can connect it over here. And that's it. Now we can again go to the PLC here, compile it in the simulator. We load the program to it, go to the name, start the monitoring. We run the PLC here. Now once I press any of the switches 0.0, 0.2, now as you can see I switched it off, but the current is still going towards Q1 24.0 from here. So it is being latched. So for delatching it, I'll be using 124.1. Once I press 124.1, your PLC will be, output will be switched off. Okay. Any problem here? Issue?
No, sir.
No problem? Okay.
No.
That's good. Okay. Maybe now we can do the experiment of overhead time. We can implement that one with an MCR. Okay. First we have I 0.0 and we tag it with the start switch. Then we have I this could be I 124.0. There is another name tagged with I 124.0. If this thing happens to you, you can go to the PLC tags. You will see the tags that have been written over here. These are the tags that we developed. Delete them. Once you delete them, now you can retype them. Right? This is your one. Stop. And then we have Q0 124.0, which is MCR. And we latch this MCR. Already. I'll be starting with MCR. As I write MCR over here, the address will be automatically generated here. We had low element sensor I 124.2 and name it. Another sensor that is upper limit sensor 124.3. And it is attached to Q124.1, which is a relay that is connected to a pump. And we can always latch it using its own normally open switch. Now let's see If the compilation has an error, there are no errors, that means we can compile it for the device. And we can load the program into our PLC. When it's loaded, we can actually run the PLC now. Okay. Now, once 124.0 is on, your MCR will be on. Right? Once your MCR is on, you can see your pump has started. Your pump has turned on. That means the tank was fully empty, and the water has started to flow into the overhead tank. And once the lower limit sensor, okay, I made a mistake over here.
Sir should be connected in between.
Yes, it should be connected in between. Should be connected over here. A small change, you have to go for everything again. Let's see.
Sir, did you call me?
Now 0.0 is on, pump is on, MCR is on. So at any instant of the time, if I press 124.1, that means the stop emergency stop button, the pump will be switched off. It doesn't, because I made a mistake again. I didn't mention MCR over here. So I need to attach MCR over here as well. That is MCR. If you find any mistake, please point it out. Okay. Okay. Turn on the monitor and the program. Now we see that pump is on. If I press this, it will be stopped. Yes, it does. It's fine. Let's turn it on again. So the pump is on. The first sensor to switch off will be lower limit. This one, so it switches off, and then the other upper limit sensor will be switched off once the tank is fully filled. At that instant, the pump is switched off. So once you drain out the water, the level is going to decrease. The first sensor to go on will be the upper limit sensor. It is turned on, but the motor is not turned on because the current is not reached the relay. So water levels start decreasing to the lowest point. Once the lowest point is achieved, pump turns on again. Okay, so this process will be going on again and again and again, and it's fully automated. If you connect the sensors, it is fully automated. Okay, any question?
No, sir.
No? So everything is fine until now?
Yeah.
Good.
Yes, sir.
Switch it off, and this is fine. For the other questions, like AND operation or operation can also be implemented over here. So we can implement basically like this.
And sir, should we include all of these in the report? All those experiments?
Not all those experiments. I will let you know. We will be doing how many classes are left basically?
2.
Two more. That
Yeah.
means yeah,
Next week
18th and
we're done.
19th.
Yeah.
And how about the communication electronics? How many classes? Two also.
Yeah, 2 also. This Wednesday and the next.
Okay. All right. We have two classes to go through. All right. Uh, there are only then two practicals left. Uh, one we will be dealing with the electric control. We will just visualize it. Okay. The actual, you know, implementation of it. I will be sending you the video so you can see the implementation part, how it can be implemented. But that experiment, we will be doing it on via portal for the pneumatic one, and there is another one, another experiment that is related to the timers. So I'll introduce timers to you next week, and in the last class we'll be going through some HMI stuff. I will show you how you can interface an HMI with a PLC, and that will be it for our course. Okay.
What is HMI?
HMI is a human machine interface.
Oh,
It's like a small monitor that is connected to a machine, from which you can operate the machine, like giving the parameters to it, and sometimes it is also used as a start stop. You are getting some information from the machine,
yeah.
like there is some fault coming in the machine. You can know there is the fault from the machine. On HMI, it will be visible to you. But this is the part that is creating the problem. Please check. So this type of information that basically comes on HMI. So it's basically an interaction device which takes input from the human and takes that input to the PLC.
Okay.
Okay, basically that's a talking device. It's a communication device, you can say, between a human and a machine. Okay,
Yeah.
so okay, just wait a second. If you remember that once I showed you this figure, this was also in your midterm, if you remember. And I asked you
Yeah.
to develop relay logic diagram for uh, this machine, right? So
It
this
was one of
thing
the
can be
experiments.
what?
It was one of the experiments that we done.
Yeah, it was one of the experiments, and that came in your midterm as well. So this experiment we can implement on the diagram as well. diagram for it. Maybe this can be your homework. You can think about it, how it is working, and how you can develop a diagram for this type of machine.
Okay.
Let me
I think it will be much easier than the pneumatic system.
yes, it will be much easier, very
Yeah.
much easier. And because you have four sensors over here, right? You can
Yeah.
attach these four sensors anywhere you want in your ladder diagram. Literally anywhere you want. Okay. So the sensors will be directly connected to like I124.0. This S1.1 will be connected directly to 124.0. S1.2 will be connected directly to 124.1, and you can reuse 124.0 or 125.1 or 124.1 anywhere in your program.
Yeah.
In the relay logic control, if you remember, if you wanted to use this sensor at multiple times, you had to use a switch of a relay. Remember,
Yes.
here you don't have to do that because this is an input, and the input can be directly connected in
Okay.
PLC.
I
Okay.
will try.
Yeah, you try it. If you don't have the software, try it on paper. Uh, Try to come up with a solution. If not, in the next class, definitely I will give a solution to it. We will discuss this experiment, and there is another experiment using timers. I'll introduce timers to you. Okay. One last thing before terminate this class. Maybe we can discuss it on the software as well. There is one more thing that we can do over here. If you see over here that I'm writing Q124.1, right? Let's suppose uh, there is one more thing that we can do over here is that there is another thing called a memory coil. Okay. Now this Q over here, these are physical outputs, right? Physical output means that these are available to you on the PLC. These are screw terminals available to you, physically available to you, right? But talking about the memory coil are basically usually there are so many in number, maybe in thousands or lakhs. You can use as depending on your logic. So based on that memory coil, you can always, let's suppose you have a complex logic diagram. You cannot use your sensors, you cannot direct your sensors to the output. In that case, you use a memory coil. So let's suppose how to do it. What is the syntax of it? I'm just going to use it over here. Simple M0.0. So if you want to use more memory coils, it can be 0.1, 0.2, 0.3. This memory coil can be used to activate any physical output. Okay, so now all the inputs that are coming to the PLC, based on those inputs, the memory coil will turn on. Okay, the memory coil is basically a virtual relay inside the PLC. It is not an actual relay. but the status of this relay is being used in another network to turn on an actual output. Okay, so the functionality of the program will remain same. The reason why we have done this over here, we have done this for no reason over here, but there are some complications when you do some scenarios, and in that case you require some relays. Okay, so let's suppose how should I say it? There is a scenario. Let's suppose that uh, once if the tank is empty, the pump should be on, right? So you can introduce a timer over there that once these two sensors are on, a timer should be on for certain seconds. After that, the pump should be on. So in that case, this memory coil will be helpful to you. So once your M0.0, the timer runs off after a few seconds. Once the timer is finished, it will turn on M0.0. Okay, and that M0.0 can be used to turn on the pump. Or it can be vice versa as well. That once your upper limit has been reached, you turn on the timer and you turn off your motor after certain seconds, maybe 2 or 3 seconds, someday later. The scenario can be anything, but I'm just making this thing up so you can understand the usage of the memory coils. Okay, so is it understandable? Is it all right until now?
Yeah, it's very clear.
Okay. All right.
And sir, the memory coil, we can use it in other networks, not like the Q output.
Yeah, the memory coil can be starting. It has to start with M. M means memory, and then
Yeah.
number you can name it any number like 0.0, 0.1, 2, 3, 4. You can
Oh,
also start with 1.0, 1.2, 1.3. Okay. Uh,
yeah.
it can be like this, uh, let's suppose there is a machine, it has two operations. Like there is a thermos. Okay, thermos has two operations to cool down, and let's suppose it is condensing at one point, and at other point it is making the temperature high, or it's boiling the water. Let's suppose it has two operations, right? So let's suppose if you are using memory coil in the cold operation, you will be using 0.0, 0.1, the sequence of 0. When you are using the hot category uh, program, in that program you will be using M1.0, 1.2, 1.3. You can always use 0 over there as well. But to differentiate or make things easier for you for the readability purpose, we change the tag. Okay, instead of going with 0 tag, you will be going with 1, 2, 3, 4, 5, 6, like that. And like over here, one more thing. In program blocks, you see main over here. This is the main program. You can always you can add another blocks as well. Okay. Once I click as blocks, over here you have organization block, functions, data blocks. The timers, counters, they come in data blocks. But the function block and function and organization block, these are the main things. Okay, organization block means like the main program. A function block, this is a block in which you create a small program, and it can be called in the main program at any instant. It has the same operation like in Arduino or in any other language. Like you have a main program and you have a function defined at another place, and that function is doing some special work. And if you want to call it in your main program, you just write the sequence and it will be called at that instant. So it does the same thing. Okay, the function. The function block over here, it is same like a function, but it has a memory. Okay, memory in a sense that uh, the output of that function block is basically saved into a memory, right? The normal function, if you use a normal function, and that normal function, once it is executed, the data will be destroyed. After that, once you use it, after that it will be destroyed. Once you, if you again call it in the main program, it will be called, but again, uh, it will be executed once. After that, there will be nothing left in the memory in regard to that function. Understand? So there will be no memory associated for this function, but for the function block, there will be a memory associated. Okay. Now these functions or function blocks, now if you want to add them, you can name them, and you can select the language over here as well. There is a ladder diagram, there is FPD, then STL. These three I know. The fourth one, SCL and graph, I don't know, and I don't know how to program these two types. The ones that we are going to study is the ladder diagram, and these are the two things that we are going to study. Perfect. So why I was telling you this, that if you want to add another function to the program, you can add another function like this block one, and I want it as a function block. Once I add it, it will be added over here. Okay. Now there will be a new program. So if for the readability purpose, if I want to use the memory file over here, I can use, but I'll be using, instead of zero sequence, I'll be using M1.0, 1.1, 1.2, 1.3. If I add another block, then I'll be using M2.1, 2.2, 2.3 like this. Okay. You can use the zeros as well if you want, but for the readability purpose, it is good that you change the sequence. Okay. Okay. Is there any issues? Any questions until now for today?
No, not really, sir.
All right. Okay, then maybe we can terminate our class for today. We will continue this next week with timers and counters, and obviously there are some logic operations like comparators, some math functions. We will implement those in the next upcoming classes, and hopefully
Okay.
you will enjoy this. Okay.
Actually, long time ago, one man asked me if I know how to deal with these things, like PLC, and he works in a factory.
Okay.
Yeah.
Okay. So after this course, you will be able to do something about it.
Yes.
Okay, that's good. All right.
Yeah.
Then maybe we can terminate our class for today. Hopefully, see you next week.
Thank
Thank
you.
you, everyone. Bye bye.
Thanks.
Bye.
Bye bye. Have a nice day.